Now the topic is Fibonacci series. So here we will learn what is Fibonacci series, and then we will devise a recursive definition and we will write a recursive function for that one, and finally we will analyze that function. So let us start. See, this is a Fibonacci series. The zeroth term is 0, next term is 1, then 2, then 3, then 5, and so on. So how we are obtaining these terms? Each term is obtained by adding previous two terms. So that is 5 plus 8 is 13, and this term is obtained by adding these two terms. So initially, what are the terms? These are the starting terms. Means if it is 0th term, then it is 0. If it is a term 1, then it is 1. Rest every other term is obtained by adding previous two terms. So initially you must have two terms, then only you can define like this, that every term is obtained by adding previous two terms. Alright, so this can be defined mathematically. Fib of n can be defined as fib of n minus 2 plus fib of n minus 1 when n is greater than 1. If n is 0 or n is 1, then if for 0 it is 0, for 1 it is 1. So if n value is 1, the answer is directly 1. For n is 0, the values are directly 0. For n is equals to 1, answer is directly 1. Otherwise, add previous two terms. So let me put it in a table. Now this is term number n and this is fib of n. Suppose I want to know fifth term, answer is 5. If I want to know seventh term, answer is 13. So first let me write a recursive function for Fibonacci series. Based on this recurrence relation, or based on this recursive definition, I will write a function integer fib of integer n. So here it says that if it is 0, return 0, if it is 1, return 1. So it means if n is less than or equal to 1, return n itself. Means if n is 1, return 1, if n is 0, return 0. Otherwise, return fib of n minus 2 plus fib of n minus 1. This is a recursive definition. That's all. If you want to find out any term like 7th term or 10th term or any term, you call fib of 10, you get the 10th term of Fibonacci series. Call fib of 7, you get 7th term. We'll come back to that function afterwards. So first of all, let us write a iterative version, that is a function using loop. So let me write a Fibonacci function using loop. Integer fib, I'll give the name fib once again, same name I'm using here. Then if the number is less than or equal to 1, then return the number itself. So here, if n is less than or equal to 1, then return n itself. Right? Otherwise, I need two terms to add them one by one. So integer term 0 is 0 and term 1 is 1. And also I have to add the values. So for addition, I will take sum s. So I have three variables. Now using these three variables, I will write down a loop for finding out nth term. See, suppose I have to find 7 terms, then already term 0 is available, term 1 is also available. Then I have to obtain this term 1, 2, 3, 4, 5, 6. So actually I should generate only 6 terms. So I should perform additions only 6 times. Already I have these two terms, right? So 2, 3, 4, 5, 6, 7. That's all. So I should start from second term onwards and stop at 7th term. So whichever term I want, I should stop that. So I should start from 2 onwards. So let me run a loop for I assign 2. So I need one more variable I, and I is less than or equal to n and I plus plus. So this is for repeating the procedure for n minus 1 times, or I am starting from 2 to n. Now every time what I have to do, s should be assigned with t0 plus t1. So this term should be obtained by adding these two, that is t0 and t1. Then after getting the sum, now this should become t0 and this should become t1. So for getting the next term, so I should change this value t0 and this I should make it as t1. So t0 should be made as t1 and t1 should be made as s, and repeat this procedure. So finally a result will be in s. So this is a iterative version. So iterative version, what is the time taken by this algorithm or this procedure? This procedure takes, let us take it, this statement will execute for one time and one time. This loop is written as 1 plus n plus 1, but starting from 2 onwards, so let us say it is only n, and the things inside will be for n minus 1 times, and this is 1. So total is 1, 2, 3, 4, 4n, and minus 1, 1, so this plus 1 gets cancelled, so it is 4n, so the time is 4n, so it is order of n. Basically we wanted to know the degree, so it is order of n. So we don't want exact formula, we want the degree. You can see that there is one for loop, and for loop will repeat for n times, so the time is order of n. It's obvious from the function. So this algorithm takes order of n time. So already we have written iterative version. Now let us go back to recursive version and analyze that one and see how much time it takes, and if any improvement required, we will do some improvements in that. So I'll remove this one and then we will analyze that function. Now let us trace this recursive function for fib of 5. If we pass 5, what happens? 5 is not less than 1, so it will make 2 calls. So we know the function is very simple, so I will just go on tracing this one. So here it will call fib of 3 and there it will call fib of 4 afterwards, not now. First this call will be made, as this is 3, so it will make a call for fib of 1 and fib of 2 afterwards, not now. Fib of 1, this is the end when n is less than or equal to 1. So yes, n is 1 now. So this will not call further and the result is 1. Then here it has to call fib of 2. So I'm just writing f here for fib. Then fib of 2 further calls fib of 0 and fib of 1. Fib of 0 gives the result 0 and this gives the result 1, and they are added, result is returned, and this is added, result is returned. And here it will call fib of 4. So for a fib of 4, this is fib of 2 and this is fib of 3. Fib of 2, fib of 0 and fib of 1. So these results are obtained 0 and 1 and they are added, result is returned. And on this side, fib of 3, again this is fib of 1 and fib of 2. Then fib of 2, this is fib of 0 and this is fib of 1. So here the call is, so here the result is 0 and this is 0 and this is 1, and added, return, added, and final addition is done. So this is how a tree looks like, a recursion tree looks like for fib of 5. If you look at the functions in the order in which they are called, this is the first function call and the second call and the third call, then fourth call, fifth call, then sixth call, then seventh, 8, 9, 10, then this is 11th call, 12, 13 call, 14 call, 15. So for fib of 5, number of calls are 15. Calls are 15. Then fib of 4, how many calls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 calls are there. Then fib of 3, how many calls are there? 1, 2, 3, 4, 5. 5 calls are there. So now if we try to observe any pattern, there is no pattern here. This is 5, so this is 15. 5, 3 is 15. Then 4, 3, it should be 12. Then this is 4 into 4 or 2 into 4 plus 1. So we cannot figure out what pattern it is following. So if you want to know the time taken by this one, then assume that this fib of n minus 2 is also fib of n minus 1. So this is calling itself for 2 times n minus 1, n minus 1, n minus 1. So when a function is calling 2 times by a reduced value of 1, n minus 1, then the time is order of 2 power n. So the time taken by this function is 2 power n, approximately 2 power n. So if you observe, the previous function iterative version was order of n and recursive version is 2 power n, too much time consuming. Now, is there any method to make it faster than 2 power n? Let us observe. Now, this analysis is important. If you see the tracing tree, that is recursion tree, the value of f3, function f3 is called here, and again it is called here. f2 is called here first time, then again f2 is called, then again f2 is called. So similarly, f0 and f1, they are also called multiple times. So a recursive function is calling itself multiple times for the same values. So such a recursive function is called as excessive recursion. So yes, this Fibonacci function is a excessive recursion because it will call itself multiple times for the same parameters. This is the problem in this one. So is there any way to avoid the excessive calls and just make a call only once and utilize it in further calls? So yes, what is the method? Let us devise a method. If you want a function to retain these values so that they can be utilized here, then for retaining the values, you have to take the help of static variable, or you can also take global variables. Let us take one array, maybe a static array or global array, whatever you want, you can take it. Index 0, 1, 2, 3, 4, 5, 6, as much size as you want you can take it. So just I have taken some size, we want up to 5. Now how to write now how to modify this algorithm to make it faster? So I'll remove few things from board and show you. This global array or static array, let us initialize it with -1. -1 means we don't know the value, -1. Now, let us trace it once again by taking the help of this global or static array. First, I will show you the tracing, what modifications we can do, then we will modify our function. Let us see. Call fib of 5. Do we really need to call it? Check f of 5. -1. We don't know the answer for this. Okay, call this one. So, when it is called, it will make 2 calls. So, the first call. Fib of 3. Do we really need to make fib of 3? Yes, we have to because we don't know the answer. Then this will make fib of 1. Do we need to make a call for fib of 1? Yes, because it is -1. Okay, make the call. So once you make the call, the result is 1. So once you got the result, because this is a small function, see if n is less than or equal to 1, return 1. So return 0 or 1, whatever it is. So this is 1. So we got the answer. So change this to 1. Now we know the answer for fib of 1. Yes. Then go back. Do we have to make a call to fib of 2? Yes, we don't know the answer. Then do we have to make a call to fib of 0? Yes, we don't know the answer. Call this function. So this result will be 0 as per this one. When it is less than or equal to 1, return the same value. So 0 returns 0. So modify this also. Now we know the answer for those two. Then make a call for this one. Do we need to make a call for this? Check. No, we know the answer. Don't call this. It's not called. Yes. So avoid the call because already we have got the answer here. So this call is skipped. Then I have to get the answer for this one. This was 0 and this was 1. So this is 0 plus 1 is 1. So this answer is 1. So modify this one. We know the answer for this. Then we got this answer 1 and this answer 1 plus 1. So this is 2. So we got the answer that is 2. Then let us go on that side. Fib of 4. Do we know fib of 4? Check it. No, we don't know. So we have to call this one. So if you call this, then there are 2 calls inside. Fib of 2. Do we know it? Yeah, we know it. don't call this one. So don't call this also. So further calls will also be avoided. Then the result we know how much it is. It is 1. Fib of 2 is 1. Then fib of 3, shall we call it? Check it. No, we know the answer. So don't call this one. So then following calls will also be avoided. And the answer for this one is how much? 2. Then perform addition. 1 plus 2, this is 3. Now we know the answer for this side also, that side also, plus. So this becomes 2 plus 3, that is 5. So this, I did not update this. So now this is 5. We know the answers for all. So these calls are avoided. So if you remove those calls and check 1, 2, 3, 4, 5, 6. So it is making just 6 function calls. For 5, 6 calls. Reason 5, 4, 3, 2, 1 and 0 is also included. So for n, how many calls? N plus 1. That is n to 0. So the time taken by this method will be order of n. So time is reduced. So just now you saw that function, if we analyze, it will take order of 2 power n, that is exponential. I did not analyze it thoroughly, just I have told you that it takes 2 power n time approximately. That is upper bound, 2 power n is an upper bound. But now by storing the result of the function in an array, we have reduced the excessive calls and the time is less than 2 power n and it has reduced down to just order of n. So a big change in the time complexity of Fibonacci function. So this reduction in time is because of storing the values in an array, holding the results so that avoid excessive call. So this approach is called as memoization. Storing the results of the function call so that they can be utilized again when we need the same call, or avoiding excessive calls. This approach is called as memoization, means storing the results. So this is applicable here in Fibonacci series. So I have given introduction of memoization. So this is an example, suitable example for memoization. Now based on this memoization, I have to modify that function. So I will remove the function and write a better function that is using memoization. Let us write a function. Suppose there is some global array f which is initialized by some function, let us say main function. All minus 1 are filled in main function. Now Fibonacci function. Fibonacci function takes parameter n, and if n is less than or equal to 1, then in f of n store the value n and also return n. So if you observe, the previous function was having just return n, but now this function is also storing the result in global array. For memoization, it is storing in f. Then else part. Else, earlier blindly we were making two functions call, that is fib of n minus 2 and n minus 1, but now we check and then make a call. If value is not known, then we'll make a call. So if f of n minus 2 is minus 1, means if you don't know the value, then f of n minus 2, you get the result of fib of n minus 2. So here we will make a call. Similarly, if we don't know the value of fib of n minus 1 and it is minus 1, that we don't know, then make a call for fib of n minus 1 and store the result in f of n minus 1. Now we have two values, then simply return addition of these two values, that is fib of n minus 2 plus fib of n minus 1. So this version is with memoization. Assume that global array is initialized with minus 1 somewhere inside main function before the function is utilized. So that's all about Fibonacci. We have learned that it can be written using iteration, then using recursion, and the time is order of 2 power n. Then we have reduced the time by using memoization. So that's all.